integer, that you cannot write it in the sum of 2 primes, you're instantly famous. Is that an example? One counter example. And this is how a computer can be used. If you check it for the first zillion cases, you can write a paper possibly, but not be famous, not even a paper probably. Nobody gets excited. So you can confirm it for finding many cases, or you can include it. But the conventional wisdom is, you need a human to prove it for all possible cases, for infinitely many cases. This is the last frontier in political correctness. I don't watch TV, but when my daughter, who is now 27-year-old, was very young, we thought that watching Sesame Street would be good for her education. So together, my daughter Celia, and about 24 years ago, now she's 27, watched Sesame Street. And one episode that I remember was some kindergartner and the kindergarten teacher telling them about computers. And can computers think? And one teacher raised her hand and said, of course not, only humans can think. Computers can only compute, can help us, but they can never think. And the teacher said, yes, you're perfectly right. And it was really said, Sesame Street, that is the guardian of political correctness against the diversity, and even in those days it was already innovative about even gay marriages. Implicitly, the message was everybody is equal and you cannot segregate on any basis. This one last thing, they're still chauvinists. They're human chauvinists, and the thing computers cannot think. So I'd like to take issue with Sesame Street and the many other people who think computers cannot think. Well, maybe not, but they can compute so well that it may appear as though it was thinking, and there was Turing's famous Turing test. Never mind whether computers can really think. If they can fool you that they can think, that's good enough for Turing and for me. So let's now see how to teach the computer not just to discover and conjecture such Collatz-like problems, but actually prove them. And hopefully the same strategy with suitably modified would be useful in proving the original one. So here's the strategy that I adopted. I took the beautiful human strategy of ladders, Grove, Amal, and Kant, and deconstructed it. I looked and see how I can teach all the tricks that they used to the computer. So I didn't read the details, but I read the outline. So phase 1, discover the ultimate cycles empirically. This is the experimental phase. So you do experiments, experimental mathematics, to discover conjectures. This is the traditional role of computers. Just discover conjectures. So you run it in many special cases, and you make the conjecture that ultimately you always get this one of the 3 periods, 1, 1, 1, 1, minus 1, minus 1, minus 1, and the more complicated one. But now is phase 2. Conjecture and inequality of the form. X of n, absolute value, is less than or equal to some constant C1 times x of minus 1. The initial condition, I take n minus 1. Plus C2 times absolute value of x0 for some constant C1 and C2. So this is also still empirical. You just guess C1 and C2, you try with C1 and C2 small. If it doesn't work, you empirically look at orbits for many cases, and the computer makes a conjecture. Phase 2 is still completely empirical. No proof yet. Phase 3 already starts the proving. But even for the proving, we do experiments. You try to prove it by induction. So you have a statement, and you want to prove it, that A of n minus 1 implies A of n. A of n imply A of n. So here's a statement that you want to prove for every n, no matter how big. So a natural approach would be by induction. First you check it for n equals 0, n equals 1, it's easy enough. And then you want to prove that A of n minus 1 implies A of n. This is a statement. A of n is this statement right here. Since x of n is defined recursively, if you do it, you hope to get A of n minus 1. But alas, if you want to prove A of n, and you look at it, you are forced to consider another statement, B of n minus 1. If you want, so okay, so let's try to prove A of n minus 1 and B of n minus 1 implies B of n and imply A of n. They will be done. But when you try to do it by spelling everything out, unfortunately, you have to prove another one, C of n. And so on. And you can keep introducing new inductive hypotheses. But unless you are Bernie Madoff, you have to stop somewhere. So the hope is that eventually you have finally many inductive hypotheses. And the computer does everything automatically. You start with the hypothesis, the statement you want to prove, A of n. Then it sees what it needs, B of n, another one. Then it sees what it needs to be A of n and B of n. And it's very possible that you won't terminate after 100 cases. And indeed, if the statement you wanted to prove was wrong, I hope you won't terminate. Because if you do, something is wrong to prove something is wrong. But if you are lucky, it's not guaranteed. If you are lucky, it won't be a Ponzi scheme, and sooner or later you have 5 hypotheses that simultaneously you can prove by induction. So with page 4, you proved it. And now that you have this a priori bounds, x of n less than or equal to something, when we have this, at least you know that every orbit is, every trajectory is bounded. And by the Pigeonhole principle, if you go around in two-dimensional space and you walk, but it's bounded, eventually you have to wind up at the previously visited place. You eventually have a cycle. So we know that every trajectory has to end with a cycle. But a priori, there could be infinitely many cycles. For many, many different initial conditions, you wind up in a cycle, but there could be many. And the conjecture said there are only 3 of them, or slightly many in other cases. How to find them? So now let's try to characterize all the cycles. But now let's take advantage that this is a cycle. We have this previously proven, rigorously proven, inequality. X of n in absolute value is less than C1 times this. But since it is a cycle, we can do it everywhere. X of n is the last, the first will be the last. So we can take n minus 1 and n, x of n minus 1, x of n is our minus 1 and 0, and take the x of 1 as x. So we have another inequality that is true for any putative cycle like this. And together, they can work together, hopefully, to characterize all possible cycles. So what do? We want to formulate very strong necessary conditions. Since the rule depends on parity, we look at the parity sequence. Odd, even, we took the x of n mod 2. And then, once again, empirically, you look at the orbits, at the cycles the computer generated, and you take in mod 2, even odd. And you look at what you get. And completely empirically, you make another conjecture that it only has a few regular expressions. There are still infinitely many cases.